Welcome everyone to the fourth day of Qiskit Fall Fest, and today is all about noisy quantum simulation, and we have Zlatko Minev and Chris Wood for the talk as well as for the hands-on tutorial, and I am really excited today. Uh, I'll be less of an organizer and more of a student today, so hopefully, yeah. So Zlatko Minev is the team and tech lead of the IBM Quantum's Qiskit Leaf research and device design and analysis Qiskit metal teams. Zlatko received his PhD in experimental quantum computing with distinction from Yale in 2018. His dissertation work on catching and reversing a quantum jump mid-flight was selected as the top math or physical sciences discovery in Discover's the top 50 stories of the year. He continued research and tech at IBM Quantum, where he founded the world's first quantum processor design and analysis full stack program, Qiskit Metal. MIT Technology Review named Minev one of their 35 global innovators under 35 in 2020. Minev is a laureate of the Presidential John Atanasoff Award, is a Cipher Fellow, serves as a member of the executive board of the Yale Graduate Alumni Association, and is the lead and host of IBM Qiskit's Quantum Information Seminar Series. In parallel with his scientific and technological career, Zlatko built a nationwide outreach and career pathways organization, Open Labs. For his leadership, Minev was awarded with the highest public service award at Yale, the Yale Jefferson Award for Public Service. So, on to you, Zlatko.
Okay. Thank you very much, Ritajit and Vishal and everyone. And I'm really excited to be here with you guys. And also, I want to congratulate all the organizers on the massive effort and really good work with putting this together. So in just a minute here, I'll share my screen and we'll take it away. Okay, so hopefully you can see the screen just fine. Yes. So our lecture today here is an introductory one to real quantum computers. We'll have to get to know what a real quantum computer behaves like and works like beyond the idealizations that you have already studied. So we can give you a good start into your journey of programming and using real quantum machines. So in this lecture, we will answer the following question. What do you need to know before using a real noisy quantum processor? Rather than try to be exhaustive, we'll take a narrow but deep path into the world of real quantum simulations that will allow you to hit the ground running quickly and to go far. Our focus today will be on the big ideas, so we'll expose you to some math, but overall we'll focus on the bigger picture. And we'll focus on the lens of concrete and manageable small examples. The ideas will generalize, so don't be shy and feel free to ask questions as we go along. Traditionally in computer science, we always start with a hello world example. And this lecture will keep with tradition. This time, however, it will be for a real quantum processor. Here you can see a drawing, and hopefully you can see the drawing. Let me know if the slide has advanced to a picture of oh, and I think maybe we lost the screen share. So let me do that one more time, and I apologize for the slight connection issue here. Okay, so let's try that again. Okay, so I think now you can see a drawing of a modern quantum computer. This one is a superconducting quantum processor housed inside of essentially a metal can, which you can see here in the middle. To make things simple, let's say that inside the can there is exactly 1 qubit. For now, I'll use the spin cartoon to depict how much we're going to abstract away of what really a qubit actually is and how it's made. For details on qubit hardware and what the actual processors look like and how they're designed, you can go on YouTube and Google my name or YouTube my name and finds the Qiskit Global Summer School 2020 lectures. But for now, we'll just keep this picture of a simple atom. That represents a qubit that has two possible computational basis states, denoted conventionally as the logical 0 and the 1. We put this funny bracket symbol, ket symbol around them to denote that they're quantum as opposed to classical. To manipulate these states, you've learned about various operations, such as the Pauli X gate. This is perhaps the simplest operation, the not logical operation, denoted by X, and pictorially represented by an X in this box. To refresh your mind about what this does and what you've learned earlier, not 0 gives 1 and not 1 gives 0. Simple and symmetric. In addition to quantum operations, we also need some quantum to classical pieces, such as measurements, which are going to extract information from the quantum world and bring it back down to the classical world. And this is performed using a measurement apparatus, which we denote abstractly as a box like this, and we'll measure in some basis here denoted by the letter Z. And if you remember what a Pauli Z operator does to the 0 computational state, it gives a +1, it's an eigenstate, and the Z operator to the 1 state simply flips the sign. So let's, for our example and for concreteness, come up with some simple algorithm to study. Suppose we want to look at an example, an algorithm that classifies or reports if a classical positive integer is even or odd. The algorithm should return +1 if the classical parameter is even, and -1 otherwise. One way to do this is to simply flip the simple bit sequence over and over again. We apply the X gate again and again and again, flipping the spin as many times as the integer specified, and using this property of the measurement that 0 is 1 and 1 is 0. So what quantum circuit is actually associated with this picture? Well, for a depth 0 circuit or integer 0, we would have the first circuit. For depth 1 circuit, we would apply 1. For the integer 2, we would apply the X gate twice, and so on, repeating again and again and again. Now, to kind of refresh your memory with this before we get into the noisy version of it, let's start by debugging through the steps. Starting at the very beginning, of course, the whole system is in the 0 state. Afterwards, after one step, we either measure or we flip the spin, after which the state of the qubit is in the 1 state. In the case that we do measure, because we're in the 0 state, we'll always get +1. In the second circuit, where the integer is now advanced, we will instead get a -1. And so on for higher and higher orders. In other words, the expectation value of the measurement, the outcome of the measurement that's expected, as a function of the integer d that we put in, is going to alternate between -1 and +1. So what does this ideally, this very simple quantum algorithm depicted here pictorially look like ideally? Well, what happens is that we start with -1 for 0 depth, and as the depth of the circuit increases, or the integer that we put in varies, suppose we pick 60, we would have repeated 60 X gates. That would have flipped the spin 60 times, and we would have ended up in the expectation value +1. And you notice that even and odd integers d correspond equally with +1 and -1. So this is nice because in effect, this will perform the algorithm and we'll get the right device. And this is exactly the picture of the cartoon spin flipping up and down. Now, let's take this and run it on a real device and see what comes out. So let's go to one of these latest quantum machines over here and run this exact algorithm and see what we actually get as real experimental data. So I went ahead and did this on a real device, and here is what I found. Wow. Okay, so this looks terrifically different. This is the raw data. It looks almost nothing like the picture on the previous slide, it looks quite different. So what happened when we went to the real quantum computer? Did we do our calculation wrong? The answer is not in this case, because as you notice, as time goes on, something is happening and the signal is essentially disappearing. And our tranquil, beautiful algorithm that we put all this hard work into is suddenly seems destroyed. So rather than storing information in every possible way simultaneously with the quantum computer, really what we've seen here is in the sense that the quantum computer appears to be broken in every possible way simultaneously, if you're familiar with this old joke. Okay, so what's really going on? Well, first, I'd like to remind you of this quote by the famous physicist Asher Perez that nothing in quantum mechanics occurs in Hilbert space. It all occurs in the laboratory. In other words, real experiments are inseparable from the imperfections and features of the laboratory and the underlying quantum devices that are necessarily and unavoidably the subject of imperfections, noise that causes errors that corrupt the calculation. And we've just witnessed the first example of that. In other words, we better understand how to deal with noise, which requires us to understand what noise is. So what are the elements of the noise in this example? And in fact, they are illustrative of almost all the kinds of noise you will encounter in quantum calculations. So going back and looking over the data, the experiment, let's start from the very beginning. You see that unlike our theoretical prediction, even at depth 0, the system doesn't start in 1 or -1. Instead, it's already disagreeing with what we theoretically expected. And this has to do with state preparation and measurement error, which for short we could call SPAM, state prep and measurement. Next, you see that the data decays almost exponentially. And this is due to the so-called incoherent noise, which we'll study. And this is going to result in loss of energy and loss of information typically. Moving along to the right, you'll see that the data seems to pinch off and revive, then pinch off again. And this almost looks like an oscillation. And that has to do with the noise called coherent noise. Maybe it's a miscalibration of our gates, maybe it's some static thing that's happening. In other words, this is causing some bias in our data. And finally, you notice even at long depth and deep circuits, we still have fluctuations around the mean. Things aren't smooth as in our theoretical predictions. And that's both due to the SPAM and projection noise, which we'll touch on. And that's a fundamental noise inherent to quantum physics. So we'll explain each and every one of these in a brief few segments, starting with coherent noise, then touching on measurements in a nutshell and introducing projection noise, then talking about the state prep and measurement, and finally getting to the most significant noise known as incoherent noise, which Chris Wood will then dive into more with in the next section. And finally, if we have a little bit of time, I'll mention some outlook on how do we overcome noise, because once you get to know it, you can begin to overcome it. So the destination is the journey in this case. So allow me to start with the example of coherent noise and walk us through our simple example, and we'll get progressively more complicated. You notice here I've repeated the circuit we started with, where we repeat the X gate a number of times. To remind you what this not X gate looks like, it's created by or generated by a Hamiltonian, which looks like this, some Planck's constant times some frequency multiplied by the Pauli X gate, which has the following matrix form and the computational basis state. And the way that you get any quantum operation is you take the Hamiltonian and you evolve it in time, which is equivalent for these time-independent Hamiltonians to just exponentiating the Hamiltonian. Or in other words, we take the exponential of this matrix with some imaginary coefficient. And that's going to define the angle or the rotation of this gate, as you might have covered in your earlier lectures. In other words, this bit flip gate or not gate can be understood as the rotation around the x-axis by an angle theta, which can also be written as this exponential. And this is kind of very standard unitary quantum mechanics. The nice way to express this that ends up being very helpful is to look at the expansion of this exponential in terms of essentially Euler's formula, which tells you that all you're doing is in effect applying either the identity, you're simultaneously applying the identity and the bit flip operation to the qubit with some coefficients given by the angle theta. Now, the reason we're diving under the hood here and how this gate is actually implemented in practice is because what if this angle theta is a little bit off in our calibration? Ideally, we would like to define the NOT operation as this physical operation, which creates a rotation around angle x of a particular angle. The way that angle is accomplished is by time evolving for some amount of time t, and that's experimentally in devices calibrated so as to get the right angle pi by this equation. But what would happen if that's a little bit off? Well, visually, let's first take a look at the Bloch sphere picture of the qubit and how it evolves under this rotation. When the qubit is in the ground state, you can think of it as this arrow pointing north. When the qubit is then subjected to this continuous rotation in time, you can think of it as revolving around the Bloch sphere, following this surface path here, going all the way to 1. And we've precisely calibrated that time. And if you kept doing this, as we do in our algorithm, you're just essentially rotating the qubit around the ZY plane. And we can analyze our quantum algorithm precisely in this way, looking at what happens when we start in the ground state, when we apply 1x gate, 2x gates, and so on. The challenge comes in the following way. Suppose that we actually have a noisy gate, x tilde, in practice, which we apply, thinking that we're applying the ideal gate. But because our devices are imperfect, we're actually going to over-rotate by some little angle, which I'll call epsilon here for this example. So this rotation around the x-axis of an angle theta, if you remember, looks like this. And we won't go over all the math. I'll just lay it out here for you in case you're interested in going back through the recording and working this out for yourself and checking. Since we only have 1 hour, we're going to kind of zoom out and give you the result. What ends up happening is that because you have this extra rotation, you can take your noisy pulse and decompose it into 2 pulses. It looks like our ideal pulse that we actually want to implement in our quantum algorithm, followed by some other pulse, some other rotation. In this case, it also happens to be around the same axis, but now it's of some angle, epsilon, that depends on the error. And one thing that we've shown and is very, very useful for all of these rotations is that the rotation of the sum of 2 angles is the product of the rotations of each of the angles. So that's a useful trick to keep in your toolbox. In other words, what we have at a high level just accomplished is to say that any noisy quantum gate that's noisy in a coherent way can be decomposed into the ideal gate followed by a noise term, a noisy gate, an extra noisy gate, typically that's small. Now, I said followed by, and this is a common pitfall I'll just make you aware of, that the order in which the gates appear, x, y versus y, x, is the reverse of how they appear in the algebra. So just be careful between what you write on a sheet of paper and what you draw in these pictorial diagrams, because the order of x and y get flipped. And this is the equivalence relation you can always use to remind yourself of the connection. Okay, so suppose we do have this very noisy gate, x, which in the ideal world would look like this, but in our practical world, we actually have our ideal gate followed by, or preceded by, in this case, a little bit of noise. On the left, and I won't go through all the calculations here for us, but what you can show very easily by recognizing that the only expression in all of these calculations is x, and x commutes with itself, so everything's essentially classical, there's no non-commutativity, you can basically treat these as almost real numbers. You can then show that the total error on the unitary, or the total noisy unitary, is actually the ideal unitary that you wanted to implement times some unitary Rx of d epsilon, and that tells you the error. And the error is in fact a rotation around x of an angle that is not just epsilon anymore, but is increased by a factor d. D being the depth of the circuit, or the integer we were interested in. So the larger d, the bigger the error that you find. And that's very unfortunate, and that is something that's going to show up and we will see. And it's quite a general effect that the way these coherent errors will add up is inside the angle, and that can have a big effect, as we're about to find out. So let's put the math aside for just a second. Let's look at the picture version of all of this. Remember, in this first example, everything is unitary. The only difference is that we have a miscalibrated gate. So in fact, our ideal gate has a little bit of over-rotation. Without that, we should find that the expectation value of our measurement outcome oscillates between +1 and -1. However, because of the extra noise that's coherent in this case, the outcome no longer looks like that. Instead, you notice that we now see this oscillation. And in fact, this oscillation is precisely determined by the error angle epsilon. And you can work out the exact math and you'll find out that it's cosine of d pi plus d epsilon. So our answer, if you want, in angle terms grows linearly, but so does the accumulation of the error. Let's compare this simple noise model to the actual real experiment. Notice the similarity between the two. Notice how in the real experiment, we're seeing an oscillation that looks a lot like the oscillation that we see in this noise model. Of course, this noise model doesn't fully capture everything we see on the left. The oscillation is also decaying. That's not captured here. That's because the decay will be associated with an incoherent error. But now we can understand quantitatively also that this oscillation is precisely due to a miscalibrated pulse. And that's something we can actually go back and tune and fix. So that's really good to know. And this is a very general qualitative statement about coherent errors. So keep in mind that these coherent errors will tend to have a quadratic impact on algorithmic accuracy. In other words, the worst case error. In other words, the difference of the ideal and noisy expectation values, if you expand the difference of these two expectation values to leading order, is quadratic in the error, which will be this d epsilon. And that's also generally true that these coherent errors can penalize you a ton. So in summary, coherent errors are ubiquitous. They can be described by unitary operations. There's no loss of quantum information. In principle, all of this is unitary. We can, in the data, see oscillations. So oftentimes that's a signature, a hallmark feature. And finally, we don't see an exponential decays in the data. And instead, they just give you, because of this oscillation, you'll tend to have a quadratic worst case error to leading order. So that tells us the story of coherent errors, and feel free to post any questions in the chat. Now, in the interest of time, I'll move ahead and give us a bit of an exposure to now measurements. So we've covered the first of the class of errors, which are just due to miscalibrations and coherent errors, and given you a specific example. Now, in the next section here, we're going to look at errors in the measurement and errors in our estimates due to the measurement itself. Quantum measurement, of course, is where everything interesting and quantum happens. You must have seen this million versions of this meme on the internet of the dead and alive cats of Dr. Erwin Schrödinger. Is the cat in a quantum box dead or alive? And this has a lot of questions about the interpretations of quantum physics. Of course, the cat is fine until the measurement. In fact, all the strangeness and interesting physics of the problem comes in because of the measurement. And this goes back to a long discussion between Bohr and Einstein and Schrödinger. So pictorially, to give you a fun picture, suppose the quantum state of the cat comes in as the cat being alive and dead at the same time in an equal superposition, and that's quantum. It's subjected to a measurement by the measurement apparatus. The measurement apparatus gives out a classical bit denoted by this double line, M, which states 0 or 1, the cat is dead or alive. And we say that the wave function has collapsed after this measurement. So what is M? What can it take? How do we understand it? Let's look at a slightly more specific example. Let's say that our measurement is in the computational basis. In other words, it's going to measure, is the qubit 0, is the qubit 1, is the cat dead, is the cat alive? The classical measurements, which is a classical number, 0 or 1, is going to be denoted by M, a classical random variable, which is either 0 or 1. In quantum mechanics, the way that measurements work is we can define the outcome probability, the probability to measure M0 or the probability to measure M1 in the following way. Keep in mind that each time you do this experiment, you're going to get a different M, and that M is going to be randomly drawn, randomly picked, randomly sampled, based on what's happening to the wave function. The statistics of that variable, random classical variable M, are governed by the wave function psi through this particular set of expressions. And where does that come from? That comes from the postulates of the von Neumann postulate of quantum mechanics. So that's a postulate, and we'll take that at face value for now. So the way to determine the probability M equals to 0 of to obtain the outcome is 0 is to look at the overlap or the inner product between the ground state 0 and the wave function psi that we have coming in, and to look at the square amplitude of that, the absolute value squared. And similarly, the same thing for the one state. This is our quantum version of a meter stick or measurement apparatus, and really the rule by which we do the actual measurement. Notice, by the way, that if I sum the probability of measuring 0 and the probability of measuring 1, and I won't go through all of the math here, you will find out that this is always going to equal 1. So we're guaranteed that this in itself will equal 1. Because the way we can rewrite the expressions on the previous page is in terms of these projectors on 0, 0, and this projector on 1, 1. So bra 1, ket, bracket 1, or ket bra, excuse me. And these projectors, exactly when summed, define the identity. So notice that this construction in the middle here is exactly the identity operator, and that will help guarantee that our classical probabilities always sum to 1. So this is a technical note. And in general, the probability to find any outcome M is given by the inner product between this, it's given by the inner product between the wave function, which in fact should have been written here as psi, and this projector. So the final scaffolding we need to summarize measurements is the following. First, there's a classical measurement outcome M. For example, M can be 0. There's also the set of possible values that M can take, or the alphabet of the outcomes, which we denote by sigma, and is in this simple case only 0 or 1. In general, it can be 2 to the n. number of possibilities for qubits, or where n is the number of qubits, or it can be some more complicated alphabet. Each outcome is associated with some kind of measurement operator that we use to then find out the probability of a particular measurement m. So that's a summary essentially of almost everything you need to know about measurements. Great. Now let's put this brief reminder or brief primer into practice by looking at some particular case. So suppose first that we start in the ground state, which we can represent on the Bloch sphere as a state pointing north. We then perform some unitary action or operation, which puts us somewhere else on the Bloch sphere, maybe here on the x, for instance. And then we perform measurement in the computational measurement basis, which gives us 0 or 1. And m then is going to denote the outcome that comes out here, which is each time we run this circuit, either 0 or 1, or we get only 1 bit. And it's a classical random variable. The way for a qubit to then understand that classical random variable is exactly with the von Neumann postulate. And we can really summarize all of the possible outcomes with just one number, p, the probability, which is a number between 0 and 1 inclusively, to measure the outcome 1, since the probability to measure the outcome 0 is just a complement of p, which is 1 minus p. In other words, what we have is a coin toss. We have a classical random variable that's drawn from a Bernoulli distribution, whose parameters are determined by the wave function psi, which is itself determined by the quantum algorithm. A bit more visually, the exact same piece of information we can represent and define in a picture that looks like this, which tells us the probability of measuring a measurement outcome m as a function of the possible outcomes, which are m0 and m1. So when we have m0, for instance, here the probability is 1 minus p, and the probability is p. And essentially that defines everything at the interface of the quantum and the classical. So what can we get out in the quantum case? I won't go through the calculation. I just have it here for those who want to then pause the video and dive deeper or try it themselves. But essentially from this, the first thing we can do is reconstruct or we can reconstruct an estimator of some expectation value of some observable. For instance, if I wanted to look at the Pauli Z observable, and I let that be denoted by m hat, we could estimate the expectation value of that observable m, as written here, by looking at the classical expectation value of the classical outcomes m. And that's done by summing over all of the possible outcomes m and weighing them by their probabilities, which for this, actually for the measurement of the probability 1 is just 0 plus 1, and it gives you p. Now, that's the piece of information we do want. The cost is going to be determined by the variance of this classical random variable, or the shot noise, which you can show as the standard shot noise, or p times 1 minus p. So if you work out the variance, which we won't dive into since this is a pretty standard result in statistics, you can find out or show that the variance of this classical random bit is just the probability to measure 1 times the probability to measure 0. In other words, if we look at what the picture version of this looks like, the variance and standard deviation of the variable are 0 when the variable has no randomness. In other words, it's with certainty 0 or with certainty 1. And the variance is maximized or maximal exactly at a coin toss probability of 1/2. This is going to be important because it will help determine the sampling complexity needed to estimate some observable as a function of this probability p. Let's make this even more concrete, because what happens in practice is you never run one shot. you always run many, many shots, since each time you run your quantum algorithm, you only get 1 or 0, but you might be interested in the average value. So to find that, you then need to run 1 shot, 2 shots, 3 shots, so on and so on. And each time at the end of your quantum algorithm, a coin toss gets flipped, determined by the wave function, and you measure 1, 0, 0, 1 with some probabilities. To make it more concrete, if we had 3 samples only, so let's say we drew the line over here and stopped to go beyond, then all the possible measurement outcomes you could have are 0, 0, 0, 0, 0, 1, 0, 1, 0, so and so on. And you can enumerate all of them here since there's only 2 to the 3. Of course, if you took n shots, you would have 2 to the n possible outcomes, and that grows very fast. So from all of the measurements that we took, which we'll label with the index n, and now we have n, capital N, number of classical variables that are random, m, each one is identically distributed and also independent. We can define the sample mean of these classical random variables with the standard definition where you look at the average of all these classical random variables. And from there, you can look at what your expected mean outcome is. To give you a sense and a flavor of what that will look like, let's take the example of a coin toss with probability 1/2. And let's look at how fast the convergence, or what the convergence of the average of the sample mean looks like as a function of the number of trials that we have done, or the number of shots of our quantum algorithm that we have executed. And so here's an animation which is going to go in time, and let me pause it and go slowly. So suppose that we took 2 trial shots, only 2 shots. In other words, we could have had 0, 0, 0, 1, 1, 0, and 1, 1 as the possible outcomes. The sample mean could then only be 0, 1, or 1/2. There are 2 possible ways to get 1/2 and only 1 way to get 0 and 1, and so that's why you see this bell-shaped curve, and it's interpolated here. As you add more and more shots, you notice that there are more and more dots that are getting filled in, and that's the discretization of sort of the continuous version of this experiment. And as you increase the number of samples you have taken, you notice that the possible values you could find for the sample mean are increasingly focusing on a narrower and narrower region. And in fact, if you took the convergence of this series to infinity, this will become basically a delta function at exactly 0.5. However, because we took a finite number of samples, 101 shots here, you notice that I still have the possibility to find the value 0.6 with some finite probability, whereas the true sample mean is 0.5. And of course, this is the very familiar binomial distribution, which tells you exactly about this problem. In other words, the message here is that because we have a finite sampling effect, we're going to have a finite error on our mean just because of the fundamental von Neumann postulate. Because we have to have this discretization and this quantum sampling, this randomness will fundamentally limit the resolution on our measurement of the quantum algorithm outcome. So let's see what that looks like. You notice that if we had our previous example without any gate error, with a gate error of 3% angle, we found that in the previous example, when we had this particular error, we found an oscillation that would look like this. And notice that everything is smooth on top of this oscillation. However, we didn't yet account in our model for this projection noise. So here is an example with 800 shots where we sampled each point each red point 800 times in order to find the sample mean, and we're plotting the sample mean. Notice the difference between the two curves. Of course, the second curve now, because of the finite sampling, has this projection noise that's fundamental. It's really due to quantum mechanics itself. And that causes this kind of random fluctuations and variation on top of the data. And that's going to be part of what you see in the data. So some common questions one can more generally have to do with the fact that the number of possible outcomes you have for n qubits grows exponentially fast and is really complicated. You know, for n qubits, there are 2 to the n possible outcomes. That's a lot. And the probability distribution over these 2 to the n outcomes can be very complicated. It can, of course, also be very simple. But for a general quantum algorithm, there are many, many studies that try to understand what does the outcome distribution look like, what are some, how can you bound the sampling complexity for certain estimators given a certain unitary or certain algorithm, how fast does the convergence of the distribution happen, what are the worst case or average case errors for estimates, so on and so on, and how you connect all of the classical outcome distribution to the quantum piece. These are some of the contexts which you see in the field. A lot of this relies on various inequalities. So if you need a reference, this is a good place to look. You can take a screenshot or go to the website. And that takes us to the end of projection and measurement theory and into the world of measurement errors on top of projection noise and state preparation. And we'll have to be very brief in the next few sections in the interest of time, since we have about 20 minutes left. So
Zlatko, if I can just bulge in. So there is just one question from Kosturi. She is asking that what are the possible noise models for 2-qubit miscalibrated gates?
Yes, great question. And that is a very good question. That's something that in a longer version of this lecture we dig into. And I think I have a slide here to give you a quick example. So suppose you had 2 qubits. What could happen is that you have some unwanted 2-qubit or multi-qubit interaction between 2 qubits during that intermediate time. That, let's say you prepare each of the qubits in the plus X state with some Hadamard gates, and then you just wait idly, and then you undo that with Hadamard gates. Ideally, this should implement the identity. However, in practice, especially on the IBM quantum devices, you notice that there typically is a lot of ZZ coupling. So again, it's a rotation, kind of an RZZ, a rotation around this multi-qubit axis, which is going to give you a rotation of some angle theta that will be determined by the time you wait t. So effectively, everything we did in the first case here with these rotations applies exactly the same way. The only difference is that now your rotation axes will be multi-qubit axes. So you won't rotate around the block sphere of one axis, you'll be rotating in some high dimensional space. And the gate error here, but what I mean by gate error here is the fact that rather than implementing just x itself as an r of x, a rotation around x of some angle, that angle might be miscalibrated. Or perhaps maybe the rotation axis is a little bit off. There are many variations, but essentially we're just not implementing the unitary we thought we're implementing. So that's what I mean by gate error to that question. So hopefully that helps. And feel free to elaborate more, and we can get back to it at the end if we have time.
Yes, there are no more questions right now.
Okay, thank you very much, Ritjit. Okay, so we're going to, let me give you a high level picture for the rest of the few slides, and we'll skip some of the math. Coming back to the example of measurements, recall that with our cat state, you do some quantum algorithm, you then measure and find out the cat is dead or alive with this von Neumann postulate probability. And that's essentially our measurement stick. But suppose that our measurement apparatus is actually imperfect. Just like this ruler, it's kind of hard to see the digits here. The way to mathematically account for that and represent that, the imperfection of the measurement apparatus itself, which is this component, is to say that there's a confusion, right? Sometimes when the measurement should have given 0, actually, with some probability epsilon, we recorded 1 because our measurement apparatus is noisy. And likewise, you could have, again, sometimes when you should have measured 1, with some probability nu, you measure 0. And so now our outcome that we actually measure, I can denote by m tilde. This is the noisy measurement outcome, which is a confused version of the true noise-free classical random variable, the ideal ideal actual expectation measurement. In other words, here you can think of this also as a communication channel, where really the measurement apparatus was trying to send 0 or 1, but because of our imperfection in transmission of the information, there's some potential confusion. And if you're familiar with Shannon theory or any of this kind of probability and Markov chains and so on, this will all look very, very familiar, because essentially you can now write probability vectors over all the ideal outcomes and probability vectors on the noisy outcomes. And then there's a confusion matrix or transfer matrix or some kind of a Markov matrix that will connect one to the other and is determined by the noise. So we won't go into the specifics of that, just in the interest of time here. Instead, I'll just try to illustrate that when you do have this kind of noisy measurements, if you try to look at what you should receive versus what you want, what you actually get, you will see two kinds of effects. So let me explain. Suppose that really what we should have measured for our probability p of measuring the bit string 1 is on the x-axis. But because we have these two confusions, epsilon and nu, which have to do with 0 going to 1 and 1 going to 0, we're going to have a change in what we see. Now, in the noise-free case, we can look at this gray line, which is just the y equals, this is just the y equals x line. And that tells us what the ideal outcome is in the absence of noise. However, notice that as soon as we have some bias in our measurement apparatus, here I picked some realistic values, notice that even at 0 probability, even if the qubit is always in the ground state, so here, we will never ever measure a probability for our random coin of 0. There is going to be some bias. And in fact, the range of values we can measure will shrink. And that's true also on the case over here for 1. I think this value is given by nu and this value is given by epsilon. We will never be able to measure a non-random coin toss anymore. So what happens is that the range of values you can measure shrinks, and also it gets tilted, it gets biased. So the values you measure are now offset from where they should be. What does this actually mean for our real data and for our experiment? If you went back to our nice example, and here I've implemented a measurement noise of this form, notice how with coherent error and without projection noise, we no longer start at exactly 1 and not at -1 here. Notice that the curve, the range of the data is actually narrower than it should be. And notice, if you look closely, you notice that the center of this sine function is no longer aligned. It's a little bit shifted from the middle. And so this is what measurement bias and measurement error will do. They will contract the range of the data, and they'll also shift it up and down. So that's the experimental signature you can notice and observe. And the way all of this can be understood is in terms of matrices that look like this, stochastic matrices. The other similar effect you can have is state preparation. So what if you have a lack of control of the initial state? For instance, with some probability p thermal, instead of starting in the state 0, we actually started in the state 1, and we just didn't know. Well, if you look at the initial state and average over all the possible initial states, remember that 0 points up and 1 points down in the block sphere. And now we're saying with some probability I take a vector pointing up, with some probability I take a vector pointing down, I average them. What am I going to get? I'm going to get a vector that points up with a shorter length. That's going to be determined by this p thermal. So the length here, the shrinkage of the block vector is going to be proportional to p thermal, the probability that we're actually in the one state when we thought we're in the ground state. And that's going to reduce the amount of information in the system, because imagine if we, with probability 1/2 started in the one state, that means that the length of this block vector is going to be exactly 0, will be a point, and at the center of the block sphere, and any rotation we do will be completely useless because we'll always measure 1/2 no matter what we measure and do. So that's why state preparation is quite important. In fact, it's even more important when you have n qubits. The way that you can write the initial state on n qubits, where the noise is independent on each of them, is by writing that with some probability p or p thermal, I start in the one state, and otherwise with the complementary probability I'm in the ground state, I do some unitary and then I measure. However, if you look at the purity of that initial state, in other words, the effective length of the block vector, let's call it, notice that even for a 1% or just a small 5% probability to be in the excited state, as the number of qubits increases, let's say 50 qubits, even if you have 50 qubits with probability of each one of 1% being in the excited state, the actual length of your quantum block vector, so to speak, in this multidimensional space is now only, it's reduced by 60+%. In other words, the errors add up very quickly when you have many, many qubits, and even a small error on each individual qubit in state preparation will quickly reduce the purity of your overall quantum state. And that's something we have to think about and take into account. So with that condensed version, we're on our final section, and I have just a few minutes to give you a high-level exposure before Chris Wood digs into this deeper. So here we have incoherent noise. And let's do a quick review of what a mixed quantum state is. In other words, a mixed quantum state, these density matrices, you can think of saying, I have a box, and in that box, I have either state psi1 with some probability, or I have state psi2 with some other probability, and I just don't know what they are. I know I might have psi1 or psi2, but I don't know which one it is. And that's going to lead to a shortened block vector, just like we saw with state preparation, and it's going to generally be a negative thing, and the kind of effect that these incoherent noises will do. So in our toy model, where we have one qubit, one unitary, and one measurement, we can begin to model quantum noise, or noise in these kinds of mixed states or incoherent noise in the following way. Suppose I have some gate I want to apply, but in reality, I don't just apply that gate, I also have some incoherent noise proceeding in. How do we model that noise? Well, one way, it's called a quantum trajectory, to model the noise is to say that actually what happens every time I apply my gate is that with some probability p, actually there's a bit flip as well as my gate, which for definitiveness of example, we can take to be the identity just to keep things simple. And with some complementary probability p, we've actually applied the identity. In other words, each time we do our quantum circuit, we're not getting the same actual operation in place. We're getting some statistical mixture of operations. Each time we run the circuit, we get X or I, but we don't know whether there was a bit flip or there wasn't. And we're going to ultimately average all of the results together. And that's one way to begin to think about incoherent quantum noise, which can then be summarized mathematically in terms of expressions by saying that you have an operation, a quantum channel, denoted by lambda, acting on this quantum state rho. This is now the mixed density matrix, where with probability p, we apply the x operation on the qubit, and with complementary probability 1 minus p, we apply the identity operation. Pictorially, what does this all actually mean? Well, visually, the noise-free states of the qubit before the noise channel, lambda, just live on the surface of the Bloch sphere. They cover that, and so here it's pictured. However, after this noise channel lambda, we can think of a contraction. You notice if you work through the math or visually thought about what's going on, is that the noise, this incoherent noise, is actually shrinking the pure states into the inside of the sphere itself, unlike any unitary operation, which will simply rotate and move the states around. Here we have a very different kind of evolution, which is going to actually result in a contraction of the Bloch sphere, which results in loss of information, which results in lower purities, and generally it's terrible. You notice that the noise isn't equally bad in all directions. This bit flip noise, for instance, along the x direction doesn't do anything. So the noise also has very interesting and rich features. So qualitatively, if you took this and added this to our model, even quantitatively, I just want to show you the math here in the interest of time, adding to our 3-degree error, and we added some incoherent bit flip error of just 1%, 1.2%, notice that the effect of this incoherent error is now to dampen the oscillations. So whereas previously these oscillations had full revivals, we now have this kind of envelope or decay of our oscillations that increase with the circuit depth, d, and are determined, the rate of that decrease is determined by the probability of an error, p. So this begins to now look a lot more like our experimental data. Finally, to give you a sense of different kinds of noise channels and models you could have, and this is what I think Chris will talk more about, you could take the same prescription that we just looked at and applied for the bit flip noise here on the left, where with probability p we applied the x gate, and with complementary the identity. That's what it visually looks like. You could begin to say, okay, what if I applied with probability p a z gate instead? The action is the same, it's just the direction of the action has changed. So now the shrinkage is in a different direction, but it's still shrinking. And of course you could do that for y, and I challenge you to find out what that looks like. Why stop there? You could go even further. You could say, what if I applied the x gate or y gate or z gate or the identity gate with some equal probability? That would cause a kind of uniform contraction and loss of information. Or why even make them all the same? What if I applied the x, y, z, and identity gates all with different probabilities? That would cause a kind of non-isotropic or inhomogeneous noise profile. So finally, coming back to all of the elements of the noise we just covered, the way to begin to understand and explain the experimental data that you will see in practice as function of depth is to say that all of this stuff that happens here and throughout the beginning, especially in terms of the reduction of the contrast of your data as well as an offset in your data, is going to be due to SPAN noise, state preparation measurement error. These oscillations tend to be fingerprints of coherent error. The decay of information, or the way that these signals decay, tends to be a fingerprint of incoherent loss. And finally, the scatter in the data, this kind of fluctuations you see around the mean, are projection and SPAN noise. So that really brings us to the last summary of our lecture, where we've exposed you to essentially all of the many various kinds of coherent quantum noises you could have. And before I end the lecture, I'd just like to say, is it all so bad? And the answer is that even though this device gets bombarded with all kinds of physical mechanisms, and I won't list all of them, but essentially any of these quantum chips is actually bombarded by a ton of different kinds of noise, There are ways to begin to correct the noise and mitigate the noise, either fully or partially. For instance, there's quantum error mitigation and quantum error correction. Quantum error correction would allow you to suppress the errors in principle entirely, but it has a very large quantum cost, as well as potentially classical overhead and many challenges. And this is not something that experimentally we're currently able to do, but the field is getting very close. On the other hand, where we are currently is the ability to suppress the noise to some partial level, known as error mitigation, which allows you to extend the computational reach of your quantum calculation. If you want to stay up to date with progress in these fields and where things are, I invite you to tune into the Qiskit seminar on every Friday at noon. So, folks, I think with that, I will leave you with this quote that I always love to share with students. And since I'm exactly at my time, I thank you very much. And Ritajit, I'll take any final questions we may have.
Yes, so there are like a few questions. I'll try to summarize them. So one is that in your opinion, which noise channel will be more important, and does the noise models change based on the hardware that we use?
Great question. So there are, I can answer that at two levels. So first of all, in a real device, you have each and every one of these processes, two different levels. And it depends a little bit on your experimental device, which one will be the most significant. Generally, actually, I would say the coherent noise tends to be one of the worst, especially all of this static crosstalk. Surprisingly, oftentimes the incoherent noise might not actually be the worst thing. Oftentimes it's actually coherent noise, which you can cancel or echo or twirl away. There are many techniques to reduce it. So once you take care of calibrating your gates and getting rid of this kind of coherent noise, which it just adds up much quicker, then generally your next biggest problem is incoherent noise. And that's really hard to get rid of. That is fundamentally very, very tricky and challenging. And that's a lot of my current research is how do we overcome that? So that's an active area of research as well. So, and then after that, I would say, the measurement noise is now becoming one of the dominant ones. That's really, really bad. And the projection noise is generally the least worrisome one because you just take more shots. And it's linear in time. It scales, it's the central limit theorem. So you have to take 10,000 shots, 20,000 shots, but on superconducting quantum devices, you can take that many shots very quickly to get a very small error bar. So it's usually not such a big issue.
So there is one more, like, does the spectral characterization of the noise help in developing noise model and hence effective noise mitigation schemes?
Yeah, that's a more advanced question. That's a good one. Maybe also to the first and the second question, these four noise models here, I would say in generally a pretty good one in practice is the stochastic polynoise, which has three different coefficients. Although in theory, oftentimes people take a depolarizing noise. In practice, our noise is biased. Typically, the Z noise is much bigger and the X and Y is roughly equal. And you also have coherent noise. So that's the model here. The notice that there's no discussion here of the spectrum of the noise, which effectively is assumed to be white noise, because these are all Markovian. In other words, noise at time 0 doesn't depend on the noise at time later than 0. And if you have a noise that has a spectrum, in principle, if you do know that spectrum, you could then design a scheme, usually a dynamical decoupling scheme of some version, that would allow you to focus on that particular spectrum. Of course, there's some techniques that just scramble the spectrum and scramble the phases of the noise so that you don't even have to worry about it. So I would say it's useful if you also know how to use it. And there's also other approaches. Hopefully that helps.
So if there is time, there is one last question and one request. The request is that can you please suggest some good source to read about this noise? That is the request. And the question is that in quantum data transmission, how to calculate the sender and receiver noise when we are performing experiments in quantum systems?
Yeah, let me take it one at a time. So for references, that's a very good question. I will have these slides posted on the website here, so you can go back and have those. And we're actually typing this up as a manuscript, so that should be available as well. Beyond that, the standard reference, of course, is Nielsen Chuan, which is a little bit um, more mathematical in general in its formulation. It doesn't treat things as practically. And other than that, I think the Qiskit textbook has a lot of examples on actually modeling and dealing with noise. I think Chris Wood will touch on a lot of those as well. And finally, yeah, there's definitely a few reviews on quantum channels that would probably be very helpful. And I think I missed the second part of the question, Richard.
Yeah, so in quantum data transmission, how to calculate the sender and receiver noise when we are performing experiments in quantum systems?
Okay, yes. So there is definitely, yeah, that's a good question. I think I understand it. I did mention that you could think of the classical measurement noise as a data transfer and reception problem, this picture. And all of this here is totally classical. There's no quantum piece in it, other than the determination of what the probabilities in this first vector are. So everything after this is essentially classical. Everything before is quantum. You could have a similar description for, now you could try to make this data sending and receiving a quantum task. And, a good reference for that is probably John Watrous' book on quantum computation and quantum information in particular. And I'm not sure, sorry, was that the question?
And lastly, Kosturi is asking, yeah, which error mitigation scheme is best as of now?
Great question. So, I probably should say the one that we just published, which is known as probabilistic error cancellation, which actually learns the noise and undoes the noise. There's a pretty nice YouTube tutorial I have on that, but essentially in that scheme, what we do is we figure out what the noise is, and then how to, in this picture on the right here, you see these arrows pointing in. We figure out how to do the inverse process, lambda inverse, to undo the arrows pointing out. So that is a very, very powerful technique, and we're very excited about it. It has a cost just like any other mitigation technique as well. So I think generally, dynamic decoupling, probabilistic error cancellation, zero noise extrapolation, twirling, those are a lot of the bread and butter things. Those are kind of the main, I'd say, mainstream techniques in use right now. There's some more specific ones that you can use in various cases, but those are generally the kind of four that seem to be quite robust and quite general and quite in favor at the moment. So hopefully that helps. There's many more techniques, and I think there's no shortage of need to test and try different things, by the way. I don't think it's a solved problem. I think it's an open problem and an open question.
Okay, thank you so much. There are no more questions as of now. Thank you so much, Zlatko, for giving us your time and this wonderful presentation.
Yes, thank you very much to the organizer, Richard, Vishal, and the team, and thank you everyone for tuning in, for all the many good and wonderful questions, and stay in touch.
Thank you.
Just to clarify, I'm just a placeholder here. All the wonderful organization has been done by Rita Jeet and Devasmita here. So yeah, thank you so much.
So the Devashmita is my friend and colleague in Indian Statistical Institute. She is also doing her PhD in quantum computing.
Thank you, Devashmita.
Thank you for this wonderful talk.
Thank you so much. Thank you everyone for joining in.